solubility product is the equilibrium associated with the dissolution of a solid into ions. And it's just an equilibrium. Right? And so let's calculate the solubility of copper 2 hydroxide in water in grams per liter. Right? And so it turns out that the solubility is defined as how many grams will go into the solution, which is grams per liter, which is related to molarity. So if we know the molarity of each ions, we know the molarity of the compound. So first, to start with the equilibrium statement, copper hydroxide in equilibrium with copper 2 ions and 2 hydroxide ions. KSP, the equilibrium, would be copper times hydroxide squared. Now it turns out that for this particular, the KSP is 2.2 times 10 to the minus 10th, which suggests that this is not a very favored reaction. Products over reactants. Solids drop out. So we can draw an ice table for this, and so we'll just focus on the copper. Any of the copper that dissolves minus X will become plus X, and this will become 2X. And to figure out what the concentrations were, think how much does this dissociate? Very much like our previous problem. If we know this, we know how much dissociates, and we can plug this in and solve. And so 2.2 times 10 to the minus 10th will equal X times 2X squared. This becomes 4X cubed. Divide 4 into this, take the cube root. X is equal to 1.7 times 1.8 times 10 to the minus 7th molar. It says that that's the maximum copper concentration that would form in the presence of the copper hydroxide. It turns out that this is also for every 1 mole of this, that would be the mole of 1 mole of this. For every 1 mole of copper plus 2, that means 1 mole of copper hydroxide has dissolved. And so that molarity can be converted into grams per mole. So molarity will be equal to 1.8 times 10 to the minus 7 for the copper hydroxide. Well, if we had 1 liter, we know that for every 1 liter, that's 1.8 times 10 to the minus 7 moles of copper hydroxide, and then for every 1 mole of CuOH2, that's equivalent to 97.5 grams of CuOH2. And so we can then calculate this and find that in 1 liter, we would contain 1.72 times 10 to the minus 5th molar. 1.72 times 10 to the minus 5th grams of copper hydroxide. So anything more than that and the compound would precipitate out, less than a milligram. So now an alternate way of using solubility products what if you set the pH of this solution equal to 8? The pH was equal to 8, slightly basic. This would correspond to a OH minus concentration equal to 10 to the negative 6th molar. You can prove that to yourself. What is the maximum copper concentration available in solution? It's not written here. This is what is the maximum. Well, this is an equilibrium, so we're fixing this concentration, so we can plug that into here and solve for the copper concentration. No ice table. This isn't an ice table. If you fixed one of the ions, say the common ion effect, you can use that and some appropriate assumptions, like the amount of this is far greater than the copper, to just solve for copper, or the solubility in this case. And so at 10 to the minus 6 molar hydroxide, and so this becomes 2.2 times 10 to the minus 20th divided by 10 to the minus 6th squared, says that the maximum copper concentration is 2.2 times 10 to the minus 8th. So our previous example, just using neutral water, allowing it to dissociate by itself, it becomes 1.8 times 10 to the minus 7th. So by upping the hydroxide ion concentration, the copper goes down, as we'd expect. This goes up, the other one goes down.